Hello, good morning to everyone, and welcome to our Professorial Chair Award Colloquium 2021. I am Carl Ezra Pilario, and I will be facilitating the session for today. And to start off our uh, colloquium, let's have our department chair, Ma'am Julianne Del Rosario, to give the opening remarks.
Thank you, Sir Carl. Good morning, everyone. So again, welcome to the Department of Chemical Engineering PCA Colloquium 2021. We are glad to be joined here today by our research faculty awardees, of course, our professorial chair donors, members from the Engineering Research and Development Foundation Incorporated, ERDFI, and interested stakeholders. Good morning, Dean Manegdeg and Sir Val Reyes. Welcome po to the PCA Colloquium this year. Today's event will showcase the works of our faculty made possible by the help, of course, of our alumni, industry partners, and their loved ones. Such help is very much appreciated, especially in the context of the status of university research and development in the Philippines. University research has always been pressured by many external factors, such as funding, institutional policies, and even sometimes political. So there is also an emphasis currently on increased and rapid commercialization, and also the own long-term career or research objectives of the researchers in their own field. So, however, the list of our PCA presentations today will show that another important but usually overlooked factor is the mentoring of our students and researchers. So most of the outputs that will be presented today are actually results of theses and dissertations of our students, with some of them results of research projects done after training research fellows and scientists. As most developing countries are geared towards knowledge-based economy, it is really of great importance for the Philippines that we develop the intellectual capabilities in the country, especially in the fields of science and engineering, which will then drive innovations and technological capabilities in the country. Such progress will then prepare us when the innovations have become fully technologically and commercially viable. With this context, it has been a challenging year for all of us because of the physical restrictions imposed by the pandemic. However, our research faculty and their respective students have managed to be very productive. Most of our students are doing the research works with the work from home setup, doing computational works, doing their data analysis from home after doing experimental works in the lab. It's been very hard, but it's doable, and we are actually still thriving. So again, we thank the professorial chair donors, the UP ERDFI, and the College of Engineering for continuously supporting the department and our research projects. And at the same time, I would also like to take this opportunity to invite all of you to the celebration activities of our 70th year anniversary of the chemical engineering program next year. So I will send out the schedule of the activities soon. And with that, welcome again, and may we have a productive day ahead.
All right, maraming salamat po. Thank you very much, Ma'am Julianne Del Rosario, again, our department chair. So right now we have a lot of presenters in store for us to present their research. And I will first tell you what the schedule will be. We will have a morning session and an afternoon session. And in the morning session, this will be facilitated by Dr. Charlie Main Montealegre. And the presentations will go as follows. Each one will present for 15 minutes, and then a 5-minute Q&A portion will come thereafter. So that will be the time when anyone from the audience can raise their hands and ask some questions. So just a few rules for everyone in the room. We will keep everyone muted for the time being. And then when the Q&A will come, then we will turn on the turn off the mute for anyone who would like to ask questions. Okay, so with that, do we have Sir Charlie Main Monte Alegre in the room?
Yes, good morning, sir.
All right, so Sir Charlie, as the facilitator for the morning session, the session chair, take it away.
All right, good morning, everyone, and welcome to the Professorial Chair Colloquium 2021. Our first speaker is Dr. Marjorie Bainosa. She is the recipient of the Maynilad Professorial Chair, and today she will be talking to us about sphere-like nickel sulfide molybdenum oxide composite modified glassy carbon electrode for the electrocatalytic determination of the penicillamine. Let's all welcome Dr. Bainosa.
Sorry, Charlie, nakikita mo yung presentation?
Yes, ma'am. And I can also hear you clearly.
Naka-slideshow siya or yung...
Naka-slideshow, ma'am. I know, kita ko yung slide, yung next slide.
Wait lang, mali yung na-share. Ayun na. Slideshow. Ayun, naka-slideshow na siya.
It's loading and... not yet. Ayan, ma'am. Okay na.
Kailangan, nawawala yung screen ko.
Alright.
Sorry. Ayan. So, good morning. I'm Marjorie Bainosa and I'll be presenting about...
ma'am.
Yes.
Ayan, okay na. Alright.
May humaharang sa screen?
Wala na, ma'am. It's all clear na po. Thank you, ma'am.
May nag-mute sa akin. So good morning again. So I'll be presenting about sphere-like nickel-3 nickel sulfide, nickel disulfide, molybdenum oxide composite modified glassy carbon electrode for the electrocatalytic determination of the penicillamine. So this is a work done with Dr. Ranjit Kumar, Ganesh Dakal, and Professor Jejin Shim. The penicillamine is a sulfur-containing amino acid which belongs to the aminothiol family. So it is a trifunctional organic compound which consists of a thiol, an amine, and a carboxylic acid. So structurally, it is similar to the alpha amino acid cysteine, but with dimethyl substituents to the thiol group. So this is a derivative of the antibiotic penicillin, but this compound has no antibiotic property. This compound is popular as a chelating agent, especially for the excretion of copper and other heavy and toxic metals that can be accumulated in the body tissues, so especially of human beings. And it can also be used for the treatment of various illnesses such as the following. So for the human body, the acceptable therapeutic dose for orally administered DPA is 0.5 to 2 grams daily. So increasing the amount of this substance in the body can cause rashes in the early treatment, and it can also cause loss of appetite, polymyositis, abdominal pain, loss of sense of the taste, and other side effects. Okay, so it is important to monitor the concentration of this substance, even though it is being used to remove heavy metals from the body, to ensure that there are no side effects for pharmaceutical preparations. So there are various methods of determining DPA in biological and pharmaceutical preparation samples. And some of these include LC or liquid chromatography, nuclear magnetic resonance or NMR, spectrometry, calorimetry, and electrochemical methods. So for the electrochemical technique, it offers some advantages such as having a fast response, using less time, and then high sensitivity and simple manipulation in real-time determination. So typically the trial groups can be examined by mercury and mercury amalgam electrodes, but because of issues with toxicities and easily damageable electrode surfaces, this can lead to decrease in the sensor response. And there was a study before by Golivant et al., which reported a good performance of sodium montmorillonite nanoclay modified carbon-based electrode for the electrochemical determination of penicillamine, but it has high operating peak potential or voltage. So other studies show the development of 1-benzyl for ferrocenyl 1H 1,2,3-diazole carbon nanotube modified electrode for the electrocatalytic detection of DPA with good limit of detection but limited dynamic concentration range. Also, ferrocene modified electrodes has also been utilized for DPA determination with comparable analytical parameter results. However, these reports show limited concentration range for the detection, and then lower sensitivities and lower limits of detection. So it is important to develop electrode materials with excellent analytical parameters for DPA determination. So noble metals and other composites or metal composites are also extensively used as electrode materials. However, these may be expensive and have issues regarding supply. So it is important to find high conducting, low cost, and earth abundant electrode materials to replace noble metals. And one option also that is currently garnering interest is the use of metal sulfides. So metal sulfides recently have been popular in terms of their performance in electronic and optoelectronic devices. So some examples would be polydimite or Ni3S4, the nickel-3 nickel sulfide compound, and nickel disulfide, which are naturally occurring sulfur-rich nickel sulfide phases. So great interest in using nickel sulfide compounds in quantum dot sensitized solar cells, for instance, hydrogen evolution reaction, and even ORR, and batteries and supercapacitors and electrochemical sensors has arisen because of its conductivity and low cost. So other related studies include the synthesis of molybdenum sulfide and polydimite nanosheet composite for supercapacitor performance, which offered long-term cycle life at high current density. And then nickel polydimite nanorods with reduced graphene oxide as negative electrode material in sodium ion battery application. And then the combination of nickel disulfide with nitrogen doped porous carbon for supercapacitor. And this is for sodium ion storage. And then we have polydimite and molybdenum oxide composite showing excellent catalytic activity and stability in a study by Wu et al. So based on the above studies, so polydimite and nickel disulfide along with some support materials like graphene and other carbon-based materials and molybdenum oxide is expected to exhibit high electrocatalytic activity for DPA determination. So the purpose of this study is to investigate the electrocatalytic oxidation mechanism of DPA on the proposed modified electrode and the corresponding surface area and charge transfer resistance. So it is also the goal to test the modified electrode in the detection of penicillamine in human urine samples. So for the methodology, nickel nitrate hexahydrate, thioacetamide, and ammonium molybdenate and pluronic triblock copolymer was added to DI water and placed in Teflon-lined autoclave. After which the mixture was placed inside a furnace or oven for 200 degrees Celsius, at 200 degrees Celsius for 24 hours. And then the resulting black precipitate was washed with DI water and ethanol and dried in vacuum inside a vacuum oven for 12 hours. So the obtained final product is polydimite nickel disulfide molybdenum oxide composite. And then the material without molybdenum oxide was also synthesized using the same procedure, but without the addition of ammonium molybdate. So for the fabrication of, the next step is the fabrication of the modified electrode on glassy carbon electrode, which consists of cleaning the glassy carbon electrode using aluminum slurry, washing it with copious amounts of DI water using sonication. Then the prepared composite was dispersed in ethanol with 5% naphthalene, which is the binder. And this dispersion was drop casted on glassy carbon electrode surface with an area of 0.0707 cm square centimeter. And this was dried for under ambient conditions. So the same method was used for the fabrication of the modified electrode without the molybdenum compound. So for the results, you can see here the FESEM images of the composite with and without molybdenum oxide. So A and B is for the polydimite nickel disulfide composite. C and D images are for the composite with molybdenum oxide, whereas E and F are the HRTEM images of the molybdenum oxide composite. So we call this the images A and B show irregular bulk particles with size range from 1.5 to 3 micron meter, whereas the images in C and D show comparably homogeneous microspheres with size range from 2 to 4.5 micron meter, with some nanosheets intertwined on the surface of the microspheres. So the thickness of these nanosheets range from 20 to 40 nanometer and from 150 to 300 nanometers respectively. Images E and F are the HRTM images, and you can see that this just clearly shows the nanosheets on the surface of the microspheres. And then on the right side, you have here the we call this high angle annular dark field imaging STEM, or scanning transmission electron microscopy image. And this is important for the analysis of materials with various components. So you can see here the presence of nickel, sulfur, molybdenum, and oxygen on the surface of the material, and the EDX, which also, and sorry, it's a little small, but it should show, the peaks should represent the presence of the compound of the elements nickel, molybdenum, sulfur, and oxygen. So this method is important to show the presence, the formation of the compound in the material. And we also have the XRD patterns, which show the presence of two sulfide phases. So although the image is a little bit small, you can the image in A shows the presence of peaks corresponding to the nickel, the two nickel sulfide phases listed here, and the presence of molybdenum oxide, is not cannot be seen on the XRD because it is amorphous. So if we have an amorphous substance, then usually you can just see a very broad peak or no peak at all in the XRD. So, but we conducted FTIR study and compared the results with previous studies to confirm also the presence of molybdenum oxide. And then we have XPS, okay, where we got the survey spectra showing peaks corresponding to nickel, sulfur, and oxygen. And for the material with molybdenum, there is an additional peak in letter B, small b, showing molybdenum 3D and sulfur 2s. Okay, so I will not be discussing this in details, but the results show that the presence of, further confirm the presence of nickel 2 plus, nickel 3 plus, molybdenum 4 plus, and molybdenum 6 plus. So based on the calculations done for the binding energy differences of the high resolution spectra for nickel, molybdenum, and sulfur. So for I don't have the graph here as well, but for the EIS, we conduct we got what they call this. Okay, so we got the following RCT values, which are what to call this, the for materials showing higher RCT value. It means that lower it means lower electron transfer rate. Okay. So in this case, you can see that the last material with molybdenum oxide has the lowest lowest RCT value, meaning it has the highest electron transfer rate among the three materials listed here. And then we conducted CV, or cyclic voltammetry studies, and if you see image A, curve A, the small a, there are no peaks in the CV curve of the bare GC given the potential window here. And then after the addition of penicillamine, a small increase in the background curve was observed for the bare GC. And then the broken lines here, or the dotted lines here, represent the absence of DPA, whereas the solid lines represents the presence of 250 micromolar DPA in the electrolyte solution. So when DPA was added into the solution, the modified electrodes exhibited oxidation and reduction peaks at 0.38 volts and that's 0.42 volts. Okay, so the material with molybdenum oxide has a higher peak current response than that of the material without molybdenum oxide. And based on these CV curves, we propose a mechanism wherein the forward electrochemical oxidation of nickel 2 plus to nickel 3 plus, and in its reduction appeared at the negative sweep potential conversion of nickel 3 plus to nickel 2 plus. So this indicates that the nickel sulfide modified electrodes redox couples greatly feature in the electrocatalytic activity with the analyte, or in this case DPA. And then upon addition of the DPA, the anodic oxidation peak current increased for both electrodes. And in this case, the DPA, which is represented here as DPA with the double band connected to RSH, just to show the presence of the tile group, was oxidized by nickel 3 plus of the nickel sulfide phases, resulting in the formation of an RS star structure, which consequently forms an RSSR compound. And then the nickel sulfide phases or species are regenerated by an electrochemical reaction through a one electron oxidation process. So chronoamperometric measurements were also performed at various concentrations and to determine the operating range of the material. And based on the slope of the plot, we were able to calculate the diffusion coefficients, which are given below. And we also did additional amperometric measurements where we added 20 micromolar DPA at various intervals. And using this information, we were able to calculate the limit of detection, which was given in figure D. So anyway, these studies are conducted to determine the range of the concentration, and then to determine the LOD and the sensitivity, which are given in the slide. So, and then afterwards, we use the electrodes to in human urine samples by standard addition method, and we got values of 10.56 and 20.7 micromolar on average, with the addition of 10 and 20 micromolar TPA in the urine samples respectively. So the recovery range values are around 105%. Okay, so in conclusion, so these two materials were synthesized using a one-pot hydrothermal method, and the impedance, catalytic peak current, and other parameters were calculated, and they were compared to results in the literature, and they were considered better in terms of the parameters listed here. And yeah, so that's all. So, and the thing is, we were able to use this on testing human urine samples. So I think that's all. And so I just want to acknowledge the EPEL lab in UPD, and then the Nano EMAP lab in Yongnam, and Maynila Water for the PCA. So thank you for your attention, and I'm open for questions now.
All right. Thank you, Dr. Bainosa. And do we have questions from the audience, from our participants? All right. We have a question from Goran. All right.
Good morning po. Hello po, rinig po ako?
Yes, clear.
Sige ba. Hi ma'am, thank you po for the presentation. I'd just like to ask po yung ano po yung nag-determine ng amount po ng MOOX niyo po sa electrode, and if ever po, do you think na yung concentration niya po in the electrode has to be optimized in future studies, or ito naman po yung optimum concentration? Thank you.
Thank you, Goran. So usually we use the XPS as the basis, and then the ICP. But in this case, we were not able to check the ICP. But yeah, this hindi pa siya optimized in terms of the molybdenum compound. So
sorry.
yes. So it's good if we can still conduct studies in terms of the amount of, changing the concentration of the molybdate precursor. Thank you, Goran.
Thank you, ma'am.
All right, and that's all the time we have. Thank you very much, Dr. Bainosa. Our next presenter is going to present a linear programming model for the optimization of the biodiesel supply chain in the Mindanao Island of the Philippines. Let us all welcome Dr. Julian Del Rosario, the Lodivina B. Reyes, Professorial Chair in Engineering recipient. Welcome, Ma'am Julie. Okay, we can see your slides, ma'am. Okay,
Is it in slideshow, sir?
yes, inside show na po.
Incorrect. Okay, sige po. So good morning again, everyone. Thank you, Sir Charlie. I'm here to present linear programming model for the optimization of biodiesel supply chain in the Philippines. This is made possible by the Lodevina B. Reyes Professorial Chair in Engineering. This is a research work by a group of undergraduate students and is queued for publication in the ASEAN Engineering Journal. So to start, biofuels are known to have several advantages over fossil fuels, including but not limited to high abundance of resources, high negligible SOx emissions, lower NOx emissions, and more environment-friendly processes. In the Philippines, biodiesel is commercially derived from coconut alone. The industry in the Philippines is anchored onto the Biofuels Act of 2006, which requires the use of biofuels made from indigenous sources to reduce dependence on imported fuels. So the act introduced incentives to further encourage local production and distribution of biofuels by mandating a minimum 1% blend in all diesel fuels by 2007, which is increased to a 2% blend in 2009. So the Department of Energy followed it through with a progressive target layout of 30% by 2030. However, as of 2020, the DOE reported that biodiesel blending remains near 2.5%. Despite raw materials being sourced locally, production costs for biodiesel are still higher compared to petroleum diesel, resulting to higher market price. Thus, consumers still prefer the latter, that is the petroleum diesel. Moreover, current biorefineries in the country are underutilized, with only 38% of the combined capacity of 575 million liters as of 2017 being used. In addition, biodiesel also competes with other profitable coconut-based products such as nutraceutical creations in terms of coconut oil share, adding to the difficulties faced by the biofuel industry in the country. The biodiesel supply chain is both an enabling and impeding mechanism for the growth of the biofuel industry. Generally, the biodiesel scene is plagued by the lack of infrastructure and supporting policies needed for an efficient and cost-effective delivery of dense feedstock all year round. So 20 to 35% of the total production cost is associated with the biomass supply cost, and 90% of that is attributed to logistics. So in total, the transportation cost constitutes 18 to 28% of the feedstock cost. Therefore, researchers have developed an interest in designing an optimized supply chain, not only for biodiesel, but for the entire biofuel landscape. The problem to be addressed we have a set of sources, that is the biomass fields, or in this case, the oil millers. We allocate the coconut oil for cocomethyl ester production for biodiesel to a set of sinks, in this study, the biorefineries. The objective of the work is to secure market for the coconut oil products of the millers through optimized matching with the biorefineries. The figure in this slide is a simplified illustration of a biodiesel supply chain from raw material sourcing to conversion to biofuel and delivery to demand zones. So I will focus on the section inside the box. So the biodiesel production cost is seen to be cut down with our work with the lower transportation cost implied by the resulting optimal network. So in this work, we will use linear programming model to minimize the cost of transportation and the associated carbon dioxide emissions. This simple tool is a usual technique used in business, engineering, and operation research for strategic planning. So the objective of this work is to optimize the current biodiesel supply chain in the Mindanao cluster by minimizing the cost and CO2 emissions in transporting the biomass feedstock. We expect that this work can be a decision aid in reducing greenhouse gas emissions in the transportation sector, in finding cost-effective matches between millers and refineries that will result to the improvement in the local biodiesel industry. The methodology of this work consists of data gathering, the LP model formulation and calculations using an open source integrated development environment, PyCharm with solving constraint integer program and Excel. And lastly, the analysis of the results. So the study only focuses on scenarios wherein the mandated biofuel blend will be 5% and 10%. We also will only cover millers to refinery in the Mindanao cluster. And the data we used for this study are from the following sources. So the sources are shown in the slide. The list of recognized oil millers with their rated capacities located in Mindanao are obtained from the Philippine Coconut Authority. And 10 out of the 20 oil millers in the list were considered suppliers of coconut oil for cocomethyl ester production. So based on the information that was given to us, so those 10 were the only millers considered for this study. On the other hand, the list of biorefineries in Mindanao was obtained from the Department of Energy. There were a total of 6 biorefineries, but only 5 were operational and were considered in the study in the first case. And then the distances from the millers to the biorefineries were obtained through the driving feature of Google Maps in order to consider only routes with accessible roads for the trucks. In determining the optimal location for building new biorefineries, geospatial data is needed to effectively recommend a site for construction. So we used the geographic information system data. However, it's only from 2011. It's taken from the Philippine GIS Data Clearinghouse for each of the 21 inland provinces of Mindanao. In order for us to represent each province as a single point, mean coordinates were generated for each province using QGIS. So we considered 2 cases. The first one is when CNO or the coconut oil allocation under specified percentage of supply from oil millers. They are already specified. And then the second case is when the CNO allocation is under an increased biodiesel blend from B5 to B10 in a future scenario. So the B5 blend was used for the first case since the current biorefineries, the existing biorefineries are already capable of producing the required CME for B5. Meanwhile, B10 blend was used for the second case, considering a gradual increase in the implemented diesel blend in the country. So the assumptions that we've made are shown in the slide. So for the objective function, it was based on the model published by Fu's group. It minimizes the carbon footprint from transportation vehicles. So the transportation cost TC was calculated using the equation here. It is dependent on the fuel efficiency FE, the fuel price FP, the allocation X, and the distance D. The objective function is then subjected to a unique set of constraints for 2 scenarios with different target outputs. So the one on the left is the constraint for case 1, and on the right is that for case 2. So in the first case, the locations of all facilities of interest, both refineries and millers, are already set. On the other hand, for case 2, it calls for determination of the location of new biorefineries to be built. So the approach resembles that of a facility location problem, which aims to find the best location for new facilities based on a set criterion, such as minimizing conveying cost involved. So for the second case, we introduced as decision variable y to identify the optimal choice among a matrix of potential locations. So it will have a binary value of 1 if a biorefinery will be constructed in the location and 0 otherwise. So summarized in the flowchart diagram here is the logic followed in building the model. So we have 2 models developed actually. So one is concerned with the optimal network between the source and the sink, and the other dealing with the addition of establishment of new biorefineries. So after solving the objective function with the constraints, the optimal allocation of CNO and the optimal results for case 1 are shown in table 1 and table 2 respectively. In case 1, as mentioned, we have a fixed portion of the rated capacities of the millers that are allocated to the refineries. So the rest, they are for other applications. So meron lang fixed for the CNO for CME production. So it can be noted that this case resulted to underutilized CNO suppliers or millers. So millers M3 and M6. So these underutilized supply may be redirected to another market or new biorefineries. So in the second case, on the other hand, here's the case wherein we expected an increase in the blend, both the available CNO supply. So initially, we considered only 10 millers and 5 biorefineries. However, with those numbers, the projected market will not be met. So the oil millers that we initially did not consider were considered in the second case. So a total of 20 millers and 6 biorefineries were used in case 2. But even with those numbers, the projected demand will still be not enough. So new plants were needed to accommodate the demand increase. So for the first part of the calculations, a break-even allocation of the CNO millers to the biodiesel industry was calculated. So the break-even refers to the required percentage of the total CNO production to be dedicated to the biodiesel production, so that it will now be similar to the first case. With that, we calculated about 30% of the available CNO from the millers to be distributed to the 6 operational biorefineries. However, the allocation model returned non-zero values for underutilized capacities. So in table 3, we have shown here that we have 4 underutilized millers with that calculation. So we have to put up additional biorefineries. So in our study, to provide the necessary data for potential facility locations, so the land mass of Mindanao was discretized into respective provinces. So this was done to objectively recommend candidate location from any of the provinces in Mindanao. So only inland provinces were included in the model since the scope of the study is limited to land transportation. And with that, we obtain two possible optimal locations, which are in Davao Oriental and Misamis Occidental, respectively. So each of these biorefinery is set to open in this study with a rated B10 capacity of 40 MLPY, which is the recommended capacity from DOE. And then after that, we included these two new facilities in the calculation and recalculated the optimal network, and the results in table 5 were found. So in conclusion, the mathematical model that we have developed a mathematical model for optimization of a biodiesel supply chain with respect to transport costs using easily accessible tools, Python and Excel. And we were able to apply it to two cases in the Mindanao cluster, with one of them predicting suitable locations for construction of new biorefineries. We hope that the results of this study may serve as decision aid for planning and implementation of biodiesel systems. So for further recommendations, we still need to check and apply the findings of the proposed model to real life scenarios with more accurate data to enhance the quality of the model. For example, the distance matrix can be more refined with finer discretization instead of just 1 point for one province. And there was no sensitivity analysis done, since these are only applicable for scenario-specific solutions. So before I end my presentation, I would like to thank again Mr. Danny Reyes for providing the Lodevina B. Reyes Professorial Chair in Engineering. With that, thank you for listening.
All right, thank you so much, Dr. Del Rosario. And do we have questions from the audience? All right, so we have one from Goran. Okay.
Good morning.
Go ahead.
Rinigo po ako.
Yes, Goran.
Yes.
Hi, ma'am. Thanks po for the presentation. Curious po ako sa sinabi niyo po na yung sa case 1, 10 out of 20 po yung refineries na kinonsider po.
Yes.
Ano ba yung standards po to determine which millers are considered and which are not? Thank you.
Okay. Thank you, Goran, for the question. So we collected the list of the 20 millers, and since our application is on the biodiesel supply chain, so we want to consider those millers that are supplying CNO or coconut oil for CNE production. Yung 10 other millers that we initially did not consider, either we do not have the enough data to consider them as supplier, or we have checked that they do not supply CNO for CNE. So yung 10 lang na kinonsider namin, sila lang yung sure kami na they are producing CNO for CME production.
Understood po. Thanks, ma'am.
All right, thank you very much, Ma'am Julie. We now move on to our next presenter. And our next presenter will talk to us about synergistic generation of energy and water in remote communities, economic and environmental assessment of current situation and future scenarios. Let us all welcome Dr. Jude Michael Agarilla, the recipient of the Benjamin Chua Professorial Chair.
Hello, good morning, everyone. Just like to check first that my presentation with slides are visible.
Yes, Sir Jude.
All right, thank you very much. So good morning again, everyone. Again, I'd like to first thank the Benjamin Chua Professorial Chair for the opportunity to present this work at today's colloquium. As mentioned by our host, I'm here to present this paper, which we worked together with the University of Manchester. All right, so access to electricity, clean cooking, and safe water is identified as key for achieving many of the UN Sustainable Development Goals. While progress has been made in recent years, the rate of population growth overtakes the improvement of access in many developing countries. Planning of energy and water services in these regions is further complicated by the complex interactions of these resources within the energy-water nexus. For example, distributed electricity generation, such as production of biogas, can affect quality of water supply due to leachates from the digestate. So methodologies in systems engineering have been highlighted as effective tools for incorporating the nexus into conventional engineering design and policy formulation. However, compared to national or regional levels, studies of the nexus at the household and community scales are limited. Thus, we propose an alternative approach for considering multiple production systems working in synergy within the energy-water nexus. This approach is termed here Synergeneration or Synergen. The study combines scenario analysis, techno-economic simulation and optimization, and life cycle assessment to design economically and environmentally sustainable systems for supplying electricity, cooking heat, and water in remote communities to benefit from the synergies that exist between them. Both the current situation and possible future scenarios are considered. The base year for the current situation is 2015 based on data availability. And for these scenarios, the year 2030 has been selected to correspond to the time horizon for the SDGs. So again, our objectives here are to develop scenarios, to simulate and optimize those scenarios for both current and future systems, and to evaluate the sustainability. So the Philippines has been selected as the geographical context for the study. As in the case for most remote communities, off-grid power systems are dominated by diesel generators. The most recent household survey shows that liquefied petroleum gas, or LPG, is the preferred heat source for domestic cooking. The water sources are also shown here, where remote communities obtain most of their water, potable water, from local ground and surface water sources, or they also purchase bottled water. So the following scenarios are considered. So aside from the current situation, we have a future business as usual scenario, which considers no change in the source of electricity in the current situation. We also have the transition scenario, where existing energy and water options are still preferred, but renewable technologies are also introduced in the supply mix. The independent scenarios assume community self-sufficiency, with utility sectors operating independently of external fuel and water sources, meaning there's a phase out of imported diesel fuel, LPG supplies, and bottled water. So the hourly electricity supply in these scenarios have been simulated and optimized in the Homer software, taking into account the increase in demand for cooking and water desalination in the relevant scenarios. Following the Synergen approach, the simulation of the current design and optimization of future electricity systems considers both the residential demand and the electricity needed for local water supply. The availability of biomass in this representative community is also considered, and this biomass can either be used for electricity production or cooking fuel, and it's also the supply is part of the constraints of the model. So unlike the business as usual scenario, the power demand in the transition and independent scenarios are derived more from water production, especially desalination, than the direct residential consumption. The independent scenario, diesel is phased out, so electricity demand is supplied by solar, PV, wind, and biomass gasification. For the life cycle assessment, the analysis is based on the functional unit defined as an annual consumption of electricity, cooking fuels, and water per household. So assuming basic access to the utilities in this remote community, this is equivalent to 100 kilowatt hours of electricity, around 4.87 gigajoules of heat for cooking, and 197 cubic meters of water. So the scope of the study is from cradle to grave. So we are looking at the impacts from raw material extraction, installation, maintenance, use, and eventual end of life of these facilities. So here are the results for the environmental sustainability assessment using LCA. For the current situation, we see that in 13 out of the 18 environmental categories presented here, water provision contributes more than half of the total impacts per household in the current situation. This is primarily due to the consumption of single-use bottles, water bottles for the water supply. Despite completely sourcing their electricity from diesel, power consumption contributes only 0.5 to 13% of the environmental impacts of the household. So the total global warming potential or carbon footprint is estimated at 1.7 tons CO2 equivalent per household per year, with 51% attributed to the water supply, again, mainly because of the consumption of bottled water. So electricity contributes 6% to the carbon footprint, and the cooking fuel contributes 67% of its impact at the point of use. Therefore, we can say here that imported water and cooking fuels are the hotspot for the carbon footprint. For the water footprint or the water depletion potential, we have here 91%, which we call embedded or virtual water. So most of this water is not because of the direct consumption of our households, but because of the consumption during the production and manufacturing stages, especially again for the bottled water supply chain. The cooking fuels are also the greatest contributors to air pollution like particulate matter and smog formation here, mainly because of the combustion of solid fuels. So cooking fuels also contribute a lot to your eutrophication as well as your ecotoxicity, mainly because of the residual ash that is typically thrown to the ground or to soil. So in the future scenarios, the independent scenario is the best option, which has the lowest impacts in 14 categories. And by contrast, the business as usual is the worst alternative, where it has the highest impacts in 13 categories. The transition scenario has the highest terrestrial ecotoxicity here, while all future scenarios have better impacts compared to the current situation in air pollution, right? Like particulate matter here. The business as usual scenario also has 35% higher global warming potential compared to the current scenario, and 67% is also due to the water sector. Again, in this scenario, there's more reliance or there's continued reliance on bottled water. The introduction of renewables in the transition and independent scenario significantly reduces the global warming potential. For the life cycle costing or economic sustainability assessment, we define here the total life cycle cost as the sum of cost of electricity, cooking fuels, and water. The levelized cost of different utilities are defined as the sum of the annualized capital cost, as well as the operating and maintenance cost of each technology for each utility type. So capital cost here would comprise purchase, transport, and installation of the infrastructure using a discount rate of 10%, which is common for energy systems in developing countries. The operating and maintenance cost include both fixed and variable expenses, as well as fuel cost. So for the current scenario, the total annualized capital costs are equivalent to 107 USD per household per year, with 79% derived from the infrastructure for local water production. The operating and maintenance costs are higher at 160 USD per household year, with majority spent on cooking fuels. In the future scenarios, the capital expenditure is higher by 8 to 21% compared to the current scenario. This is due to the additional technologies that are included in those scenarios. So most significant cost items here would be the wells, the pipes, the desalination modules. The independent scenario has the lowest operating and maintenance cost, with the business as usual scenario having the highest. So across these future scenarios, the majority of the operating and maintenance costs are again attributed to the cooking fuels. For the total life cycle cost, so based on the annual consumption or the functional unit, we have here annual cost of 2,944 USD per household year. That includes this big chunk of the cost of bottled water. For the future scenarios, we can see that the independent scenario has the lowest, and the business as usual has the highest. Again, this is low because of the absence of imported fuels and imported water supply, which includes the bottled water. So we can see here that by reducing the dependence on imported bottled water as well as an imported diesel fuel, self-sufficient utility systems in remote communities are financially attractive, but will still need the implementation of new technologies such as desalination, gasification, anaerobic digestion to replace the existing energy and water infrastructure in these communities. So in conclusion, this work has presented the environmental sustainability of environmental and economic sustainability of supplying electricity, cooking fuel, and water to remote communities. So both the current situation and the future scenarios have been evaluated taking a synergistic approach. So as shown here, the cooking fuels and imported or bottled water can be greater sources of environmental impacts and costs compared to the power generation. So the development pathways that only consider installed technologies and continue to rely on existing supply chains can exacerbate these impacts. The combined analysis of these three utilities further suggests that desalination and bioenergy can enable a sustainable transition towards self-sufficiency of these remote communities. Additionally, high dependence on a specific technology or resource can pose risk in the security of supply that can affect the other sectors. So to broaden the sustainability assessment, we suggest considering also socio-economic indicators in future work. Furthermore, we can also explore the applications of this approach to other geographies, scales, and technology options. So again, this has been a presentation on synergistic generation of energy and water in remote communities. You can access the full paper published in the journal Energy Conversion and Management through this QR code. Thank you again to the Benjamin Chua Professorial Chair Award for this opportunity.
All right, thank you so much, Dr. Abrilia. Do we have a question from our participants? All right, Goran, go ahead.
Hi, sir. Good morning. Thanks for the wonderful presentation. Meron po akong question on slide 7.
Slide 7.
Yes po, yung scenarios for energy and water access.
Okay, this one?
Yes po. I'd like to ask why is there no diesel on transition and independent scenarios? Although the diesel should be decreased, shouldn't there be a remaining component that has it? in case of
Yeah.
as a backup for blackouts
So
or energy
based
losses?
on the simulation and optimization in Homer, the diesel generator still exists. So there's still the existing 100 kilowatt in the model generator, but it only contributes 1%. So it's actually there, but it's very small, so no longer visible in the graph. So it just contributes 1% to the total power supply, and it's mostly used in peak operation. So most of the electricity is provided for by the gas turbine fed by the biogas, from the gasification.
Understood. Thanks, sir.
Okay, I think we have time for one more question. Mhm. Follow-up question from Goran.
Since wala pong nagtanong, I'll ask another question. Sir, I
Okay.
think this one po is on slide 10.
Slide 10.
I'd like to clarify lang po sana yung meaning po ng negative component po sa graph on freshwater eutrophication. Does that mean that a more negative value is better, or does that mean it's ecologically worse? Thank you.
Okay, thank you for that question, Goran. So in this case, negative impacts mean a reduction of this impact. In this case, reduction of freshwater eutrophication because of the implementation of these technologies. So in the future scenarios, there is utilization of waste biomass, right? So the utilization of waste biomass would divert this waste biomass from dumping to the soil and dumping to the water, and instead uses them for electricity or for cooking fuel. So that diversion of flow, from disposal to utilization actually reduces the life cycle eutrophication impact. So this is why we see here negative impacts compared to the current situation.
Understood, sir. Thank you pa.
All right. One more question. Yeah, because we have 2 minutes left. Okay. Well, if we don't have any more questions, then thank you so much, Dr. Alvarilia, for this presentation.
Thank you po.
All right. And we may now move on to our next presenter. Our next presenter will tell us about virtual screening of 1,103 phytochemicals from endemic plants of the Philippines for the inhibition of the main protease of SARS-CoV-2. This is a very timely study, and let us all welcome the recipient of the Edgardo Pacheco Professorial Chair, Dr. Arthur Gonzalez III.
Thank you, Sir Charlie. Good morning, Dean Ferdy. Good morning, faculty and students. And good morning to all of our guests today. So I'm here to present my Edgardo Pacheco Professorial Chair Lecture on the screening of phytochemicals for the inhibition of the main protease of SARS-CoV-2. But first and foremost, I'd like to thank the donors of the Edgardo Pacheco Professorial Chair, UP ERDFI, and Office of the Vice Chancellor for Research and Development for funding this research, and of course, the College of Engineering. So as you may know, this is part of the response team project of College of Engineering against COVID. So COVID has infected more than 200 million people and have killed more than 4.5 million people around the world. And in the Philippines, it's around 200,000, 2 million infections and around 40,000 deaths. And this is caused by, we all know, SARS-CoV-2. And simply put, this is bad news wrapped in protein. No? And the bad news is the RNA genome, single RNA genome, that hijacks our cells and forces them to produce these proteins. No? Around 16 non-structural proteins: the spike protein, the envelope protein, the membrane protein, the nucleocapsid protein, and some other proteins to produce more virus particles. No? Most of these we know now their functions. And now that because that we know their functions, we can now proceed with targeting them. So in the beginning, there have been so many challenges to address this pandemic. So, but after more than a year, the scientific community have already addressed them. No? So before, there was a lack of molecular information. Um, we didn't know the structure of most of the targets, and there was some ambiguous biological data. Primarily, I would opine that it was because China was not letting us in on the secret or on the structures of these um, uh, proteins. No? And there was an incomplete genome sequence, but we already established that after a few months. And the non-availability of the crystal structures around February, March of 2020, we have established almost all of the crystal structures of the target proteins. And because we have established the targets, no, we then identified a large library of compounds to test them with. So this has been addressed already. So in the initial stages also, there was a race to repurpose existing drugs, no? Because as we can see from this diagram, this is the drug development pipeline. And if when we're dealing with the pandemic, we cannot bypass these stages for new drugs. So the strategy was to repurpose drugs already in existence, because novel drugs take time to develop, and we cannot bypass safety trials and regulatory barriers. We can speed them up with emergency provisions, but we have to identify and be sure about the safety and the effectivity of these compounds. And to establish, to help with the repurposing of drugs, repurposing of the known compounds, we can use of the structure-based drug discovery as a tool. No? So we can cast a wide net for expansion of the search space. In fact, there are some studies who have searched billions of compounds, or use billions of compounds as their library, initial library. We can increase diversity of leads, no, so that we can pick the families for each target, and we can identify tighter binders with tighter binding, meaning with high binding energies, and we can then optimize the potency of leads by changing some groups in the candidates. And then with those strategies too, we could reduce off-target effects, no? And mitigate attrition rate in the clinical and preclinical and clinical studies. The main goal of structure-based drug discovery in silico screening is really to generate a synthesis or a buy list that we can now test in vitro or in vivo and even in animal studies, and then go on to clinical studies. So let me talk about the targets, no? The few targets that the scientific community and drug discovery folks have been working on. No? So the main one really is this spike glycoprotein. I hope you're seeing this beautiful trajectory video from Schrodinger. So this is the one that binds to the ACE2 receptor in the host cell. But as a drug target, it is difficult to hit because of the changing conformational states. As you can see, it's really No, it's moving. No, it's and this is just one of the trimers. No? So although there's three of them in a bunch, it's really difficult to hit because of the changing conformations and mutations that I'll talk about a bit later. No? It is widely explored because it's a vaccine target, no? Or in some vaccine strategies we try to mimic the spike protein to produce antibodies against it and against the SARS-CoV-2. The other target is the polymerase. This is responsible for stitching and correcting the RNA produced in the host cell. It is a big target protein, so much so that we're only showing here the active region, the active site. And this is the one of the monomer of a dimer protein. It has a few conformational states, which makes it also difficult to target, but not so much as a spike protein. And it is a target of a few drug discovery studies. And in fact, this is the supposedly target of the remdesivir, which was approved for treatment a few months back, and the target of molnupiravir, which is, I think, will get approval very soon, the drug from Merck. So they introduce RNA errors in the RNA genome. A lot of errors, in fact, that the virus will not survive with those errors. And then we have another target, which is the cysteine-like, 3-cysteine-like protease. So this is responsible for cleaving polypeptides that has been produced by the host cell, and then to generate the proteins, the ones that I showed you, to make new virus particles. This is an attractive target because of its stability. More on that later. And we know the catalytic site and catalytic residue, so we can target them specifically with our lead optimization. Very similar to other coronaviruses protease. So we could potentially create a drug that can inhibit all or most of them. And yeah, potential solution for many other infections. So a note on the mutations. So I've shown you a while ago that the RNA genome codes for the 16 non-structural proteins, spike protein, and other proteins necessary for the creation of virus particles, and of course the RNA itself. This is the alpha, beta, gamma variant. This is, I'm just showing the Delta variant is very similar to the B lineage, B117 and 1351, with an exception or an important mutation, E484K. So what's this? Glutamic acid to lysine, no? Glutamine. So for the Delta, the variant, this will be Q. But as we can see from here, that the mutations, there are a lot of mutations in the spike protein. And if we are to deliver drugs to the spike protein itself, then with just one change in the receptor, in the spike protein, our drug molecules could be rendered ineffective. For vaccine, there's a little or more wiggle room. But in the end, if there are enough mutations in the spike protein, then the vaccine also will not work. But we can see from here that, so the protease is actually NSP5, so this part. And from the variants that we've seen so far, there are no mutations in the NSP5 region. So the target has remained the same from the wild type in the variants. Another note, the polymerase also doesn't seem to have mutations. That is NSP12, the polymerase, the target of the new Merck drug. So our strategy in our group we wanted to identify the phytochemicals that could be viable source of novel drugs, specifically for the SARS-CoV-2. We are known as one of the 17 mega diverse countries with a lot of flora and fauna, sorry. And the study of plants and their medicinal potential is especially relevant in our country. And our focus for phytochemicals as a source of potential compounds is in consideration of mass production and of such therapy in case of verification. So the objectives of this study was first to catalog Philippine phytochemicals and prepare the compound structures for modeling studies. Use in silico screening to identify the potential inhibitors of the protease, the 3CL-Pro of SARS-CoV-2, and eventually use the results to accelerate the screening process using machine learning. This part of the study is to be done by Dr. Remolona, colleague of ours in the chemical engineering. So we use the standard in silico screening method. So first we prepared the target protein. The PDB ID, if you're interested, is 6LU7. The difference is we generated. So at that time, 6LU7 around February was one of the first proteins to be crystallized. We were not sure of its integrity as a crystal structure. It might have changed. So we decided to get five representative structures by doing MD simulations of 6LU7. And then we prepared the compounds. So we identified 1,103 phytochemicals from various databases that are available in the Philippines. At this point, our library has more than 3,000. We have identified 2,000 more. And then we generated ionized states of these compounds, resulting in 1,800 plus unique compounds to screen. We did docking experiments on those 1,800 on the five representative structures of the 3CL protease. And then we decided on a cutoff of -8 kilocalories per mole. And then we did MD simulations, triplicate runs of MD simulations on the top compounds to analyze the stability and protein ligand interactions. And then we compared them, this was last year, we compared them to 14 quote-unquote reference compounds. So these compounds were the result of in silico repurposing studies to benchmark our phytochemicals against. And then we did absorption, distribution, metabolism, excretion, and toxicity in silico evaluation to determine the viability of these compounds. So let me present to you the results. We have identified from the 1,103 compounds, 16 candidates whose docking scores are greater than 8 kilocalories per mole. And these are those compounds. I'll show you their names later. So this is a pose of, this is the monomer of the 3CL-Pro, and this is a pose of aurantiamide, I think 1206, so one here. And we can see the pocket where this compound binds in the protein. We also did structural analysis on the docking results, and we found several amino acids, residues that bind or have interaction with the compounds. Particularly, we are interested if there is an interaction, or if there are interactions with histidine 41 and cysteine 145, in which case almost all of these compounds have those type of interactions. We then did MD simulations of the top candidates, and we did trajectory analysis. We found that all of them were stable, and no candidate, none of the 16 exited the binding pocket. We also did root mean square fluctuation analysis, and all candidates, as I mentioned, have interactions with the catalytic diet histidine 41 and cysteine 145. From the MD simulations also, we did time-dependent analysis. No? And from here, we can see that histidine 41 has at least one interaction at all times, no, during the MD simulation. So this that interaction fraction is greater than 1. That means at all times there's one interaction present. And we identified also the type of interactions. We saw charge interaction, hydrophobic interaction, which is very important for drug delivery or as a drug interaction. We saw pi-pi stacking and some hydrogen bonding, H bonds, green here. Right. I'm loath to show tables in presentations, but I think this is a very important table to show. And I also apologize because I noticed a while ago that the watermarks make reading the slides very difficult, but these are the chemical names of the top 16 compounds and their sources that are present in the Philippines. I'd like to show the human oral absorption here, that for our thiamide, it's 100% can be absorbed orally, and our thiamide acetate is 95.3% can be absorbed orally. Some of the candidates here we just rejected because of zero human oral absorption. Those that have less than 50% are also not recommended for further studies as of this moment. So to compare to the best results of other simulation studies, so we can see here the glide scores, and from the glide scores of our top compounds, they are comparable to the to other studies, and their energy of binding is also comparable. So around June, July last year, we were pretty happy with the results, comparing our results to other simulation studies. So in conclusion, we use structure-based drug discovery methods to identify inhibitors of 3CL-Pro. We have identified 5 compounds that are strong candidates. So they are thiamide acetate. I always have difficulty pronouncing this, isoliquidtiginin, lutein, and apigenin. And these 5 compounds are recommended for further lead optimization in vitro studies or even in vivo studies in the future. But let me share with you so that you can understand the limitations of these studies, that the energies we calculated here do not represent actual binding energies. We need to do calorimetric studies to be able to do that properly, but they are very good approximations. For this, we use GBSA methods. The results also provide snapshots of the interaction. And just to warn you, a caveat that 95 to 98% of drug discovery studies fail, but really we need just 1 or 2 to work. So that's why we need a broader search space. No? And in the Philippines, we are a bit behind in funding and infrastructure to perform researchers like these, but I believe we have the talent to do this. And so what's next? This is not the first nor the last pandemic. All of these viruses caught us and diseases caught us unprepared. But the incentive to risk ratio to develop vaccines and cures have been proven to be high for many pharmaceutical companies, albeit at a terrible cost to human lives. Research should be initiated by government institutions and the academe, and the program should have an industry partner to quickly test and manufacture successful candidates. There are two ways to do this. No? We can still do repurposing of available drugs and phytochemicals and to design new drugs. So I call on our donors that are present here. Sana po hindi kayo magsawang mag-donate sa mga studies na katulad nito so that we can continue our work. Thank you, everyone, and I'll be happy to answer any question.
Thank you very
Charlie?
much, Sir Bo. Unfortunately, we do not have time for questions, but I'm sure you
I'm
can just
sorry.
ask.
Yeah.
Yep, you can ask Sir through his email or through the chat. It will be fine. All right, thank you, Sir Bo. These are very interesting results.
I'm so sorry. Didn't see the clock. All right. Thank you, guys.
All right. Thank you, sir. And without further ado, let us welcome our next speaker, who will talk to us about the evaluation of an ion exchange membrane functional groups and investigation of temperature effects on AEM water electrolyzer performance for hydrogen production. This will be delivered by the Maynilad Professorial Chair Award recipient, Engineer Christian Julayap.
Okay.
Let us all welcome Sir Julayap.
So thank you very much, Dr. Monte Alegre. So good morning, everyone. I hope you can hear me clearly and you can see my slides.
Yes, sir.
Okay, so today I'll be presenting the work of Ms. Depano, Mrs. Cotto, and co-advised by Dr. Rizalinda De Leon. So the study is titled Evaluation of an Ion Exchange Membrane Functional Groups and Investigation of Temperature Effects on AEM Water Electrolyzer Performance for Hydrogen Production. So I would like to acknowledge the Maynilad Water Services Incorporated for making this research possible. And this research was done just last academic year, so during the pandemic. Okay, so to start, so hydrogen is abundant and is the most available renewable energy. It is considered as an excellent energy carrier to generate power for domestic, industrial, and automotive purposes because it can deliver and store tremendous amounts of energy. It can be produced from diverse resources including fossil fuels, biomass, and water. At present, on an economical basis, so the world strongly depends on fossil fuels for hydrogen production, and in order to attain sustainable development, the shift into a clean, renewable, and economical alternative fuel is a matter of urgency. Thus, with this, hydrogen production can be alternatively done through electrolysis, where water is converted to hydrogen and oxygen in a single step using electricity, which can be generated from renewable sources. Water electrolysis is one of the cleaner technologies that is attracting increasing attention because of the hydrogen purity. So depending on the kind of electrolyte and the operation temperature, water electrolyzers can be classified into three main categories, or in terms of technologies. We have their alkaline, proton exchange membrane, or PEM, and solid oxide electrolyzers, or SOE. So solid oxide electrolyzers operate typically at temperatures above 500 degrees Celsius with water in the form of steam. On the other hand, we have alkaline and PEM electrolyzers. So these operate at the low temperature range, which is typically below 100 degrees Celsius, where water is liquid. So we will be focusing on these two since we know that in the normal conditions, water is in the liquid phase. So comparing the two electrolyzers, so the issues that arise on alkaline water electrolyzers are the limited temperature range, low current densities leading to corrosion, and durability problems. For the case of PEM, or the proton exchange membrane, while it operates at a higher current density, a greater temperature operating range, and a higher purity, they are more costly due to the titanium-based contact elements. So you have your polymer membrane here with the, again, the contact elements such as the bipolar plates and the current collectors that are used. Thus, we want to try to combine the two technologies, the PEM and alkaline. So we have now an ion exchange membrane water electrolysis. So it utilizes the lower cost electrode materials of alkaline water electrolyzers and the greater energy efficiency, compact design, and higher production rates in terms of current density per unit electrode area of PEM electrolyzers. However, it is still a developing technology and consequently needs improvement in terms of performance, such as alkaline stability and low hydroxide conductivity. So the AEM is one of the chief components that determines the performance of the electrolyzer. Its function is to transport hydroxide ions from cathode to anode and to act as a barrier for electrons and gases that are produced by the electrochemical reaction. So an ideal AEM possesses the following characteristics as shown. So you have your adequate chemical stability, high hydroxide conductivity, good thermal stability, sufficient mechanical stability, and excellent long-term durability. Among these criteria, high hydroxide ion conductivity and chemical durability have been considered as the most important properties for use in practical systems. These can be attained by choosing the suitable functional groups for the AEM. The polymer backbone is mainly responsible for the thermal and mechanical stability. So at this point, we want to address the low hydroxide conductivity and poor long-term alkaline stability of AEMs, which are their major limitations. So speaking of functional groups, so they're accountable for the ion exchange capacity, ionic conductivity, and transport number. So it is responsible for the transport of hydroxide and ions and minimizing the amount of hydrophobic group. So shown are the typical functional groups, so on the left. And so far, there's no consensus on the best AEM as each functional group has its own strengths and weaknesses. So for the study and due to data availability, so the functional groups are narrowed down into three, so which are imidazolium, piperidinium, and quaternary ammonium. So shown in this slide are the degradation pathways of the functional groups after exposure to alkaline environment, since the hydroxide attack may reduce the conductivity of the membrane. So we look on the gaps that are observed while doing this research. So some of the gaps observed are number one, so there's lack of established mathematical methods on AEMWE, since based on the development of PM and AEM water electrolysis models thus far, a portion of its mathematical model was derived from fuel cells. Also, we consider the poor chemical stability of AEMs, so we need to identify a suitable polymer backbone and functional group for various properties such as ion exchange capacity and ionic conductivity. Lastly, we consider what if we have their large-scale production of hydrogen. So using the AEMWE technology, we have this problem in terms of high production costs due to power supply. And note that 41% of the energy use comprises of power supply and control costs in hydrogen production. So with this, we set the objectives of this study. So we want to design an ion exchange membrane water electrolyzer for hydrogen production. The specific objectives are as follows. So we want to evaluate its membrane properties and the stabilities of AEM with various functional groups, and we narrow it down to three. We will try to predict the performance and efficiency of each membrane based on its ionic conductivity in AEMWE at two operating temperatures, which are specifically at 20 and 80 degrees Celsius. And lastly, to recommend a suitable functional group that will improve the overall performance and efficiency of AEMWE for hydrogen production. So some scope and limitations. So we limit the investigation on the performance and stability of functional groups. So we do not include the polymer backbone. And then we only considered 1D membrane electrode assembly. And we've based our data and mathematical models purely from published studies only. Okay, so for the overview of methodologies divided into four, so we have the data gathering from journals, and then we have your membrane properties evaluation. The third one is we are to simulate the AEMWE at varying temperatures from 20 to to 80 degrees Celsius. And lastly, we simulate the various membranes at the set conditions. So for the second part of the methodology, we use Microsoft Excel. And for the third and the fourth one, for the simulation proper, we used MATLAB. Okay. So for the data gathering, so we use data from journals. So for the membrane properties per functional group and polymer type. For the physical-chemical parameters, so this is in terms of the anode and the cathode. We have the operating condition parameters. And lastly, you have your structural properties of the membrane electrode assembly. Then we continue. For the membrane evaluation, so in order to recommend a suitable functional group, so the properties of the membrane must be evaluated and compared. So qualitative and quantitative comparisons will be done. So please take note that for each property, so it describes the membrane stability. So seen on this table, so for example, the ion exchange capacity and the membrane conductivity describes the chemical stability. The Young's modulus and tensile strength describes the mechanical stability, whereas the percent water uptake and percent swelling ratio describes the dimensional stability. So again, qualitative and quantitative comparisons will be done. So the data will be normalized, then will be plotted in the radar chart to qualitatively derive comparisons, and the performance will be ranked quantitatively by calculating the area of the radar plots. For the models to be used for the simulation, so we consider the mass transport equation for gases. In setting the boundary conditions, we take note that for interfaces 1 and 4, so the liquid saturations are set to be equal or the same. And then for interfaces 2 and 3, we consider the oxygen and hydrogen evolution respectively. Electrochemical kinetics will be described by the Butler-Volmer equations in the anode and the cathode electrodes. For the cell voltage, so we calculate the applied voltage through the sum of the resistances, including the Nernst potential. And for the Faradic efficiency, so we relate that with the voltage loss and the voltage applied from the equation above. Now, for the membranes in AMWE simulation, please take note that we are to vary the membranes. And in order to vary the membranes, we want to manipulate, or at least we want to check one property of it, which is ionic conductivity. And we will be using only this property to vary the membranes. And the ionic conductivity data are available for 20 and 80 degrees Celsius only. Okay, so for the results and discussion, so we look on the characterization of your various anion exchange membranes. So based on the 3 functional groups, and based from this radar plot, we can see that the imidazolium has the best mechanical stability and good dimensional stability. And for the piperidinium has the best ionic conductivity, best alkaline stability, and best chemical stability. And lastly, for quaternary ammonium, compared to the first 2 functional groups, it has poor properties. Okay. Then radar plots of the specific membranes under each functional group are shown, and it shows the individual performance of each membrane relative to its functional group classification. So for the EMEE simulation, so 5 types of plots were extracted and separated to compare the effect of operating temperatures. The first one here on the left is the polarization curve, which relates current density to the applied voltage. Then we have the efficiency of the EMWE. So from these plots, we can see that by increasing the temperature, it improves the overall performance of the EMWE, given that less voltage is needed to be applied to accomplish the same production rate and increase in efficiency. Then this is further exhibited in the next set of plots, which show the losses such as the ohmic loss and the overpotentials of anode and cathode. So the overpotentials are due to your half cell reactions, and they contribute more voltage loss compared to the ohmic loss. And normally, the ohmic loss is mostly caused by the ion transport in the membrane, thus increasing the ionic conductivity of the membrane may lower the ohmic loss in the system. So for the membrane simulation, so as mentioned earlier, so the model only accounts the ionic conductivity of the membrane. Thus, this is the only varied membrane property for the simulation to predict the performance of each membrane at the chosen operating temperatures. We look at the three functional groups. So for the piperidinium functional group results, so from the membrane evaluation chart, so the PTP90, which is represented by the orange polygon, is expected to perform the best based on its properties. And this expectation was met when simulated as shown on the performance plots to the right as represented by the red plot. However, we can see inconsistencies to the remaining two functional groups. For example, for the quaternary, we can see that for the 10-7 membrane type is better in the radar plot, whereas in the simulation runs, the 10-18 membrane type is the better one. And then also same inconsistencies can also be observed for the imidazolium functional group. So kindly take note that with these inconsistencies, there are other membrane properties, although important, were not incorporated in the math models. Thus, these were not accounted for in the AMWE performance. Nevertheless, by ranking the membrane summary, still the piperidinium is still considered as the best membrane functional groups out of the three. So conclusions, we have evaluated and characterized qualitatively, so through radar charts, and quantitatively through area plot calculations, the membrane properties and stabilities of AEM at various functional groups. We also have predicted the performance and efficiency of each membrane through mathematical models and polarization curves. And based from the qualitative assessment and even with the simulations, so the piperidinium functional group is the suitable one which exhibited the best overall performance and efficiency of AMWE. So some recommendations, so maybe can be further described or simulated using a better software such as COMSOL Multiphysics. We may want to incorporate other properties such as the mechanical properties, so to better describe the model. And then maybe we can add or improve existing suitable membrane functional groups by doing wet lab experiments, which limits what we can do nowadays. And then maybe lastly, we can investigate further the piperidinium functional group. We test its stability in different conditions like higher temperatures and current densities. So with this, again, I would like to thank the Maynilad Water Services Incorporated for this Professorial Chair Award. And with that, I end this presentation. Thank you very much.
All right, thank you, Sir July. And do we have questions from the audience? From our participants? Yep, we have one. All right, go ahead, Goran.
Hello, Goran.
Hi, sir. Curious po ako sa choice niyo po ng properties. You did mention po near the tail end of your presentation that there are other properties that could be accounted for. If you were to repeat the study or expand on this, the same methodology, what would be the other properties that you would include aside from the 6 that were mentioned?
Ayun, as mentioned, particularly dun sa may recommendations, kasi take note that we've only considered the functional groups, but we also need to consider yung sa polymer backbone. And to assess din yung parang the performance of the polymer backbone, we need to consider the mechanical stability also. So for the mechanical stability, kasi yun nga, if exposed to high alkaline environment, so we can see some possible degradations. So therefore, we can look at some mechanical properties. So I've mentioned in the recommendations. So maybe we can include in the math models or to update the math models in terms of including for example, the mechanical properties such as the Young's modulus, the tensile strength, the swelling ratio. However, due to data availability na din, so we've only considered muna for now yung sa functional groups. And also we wanted to look with the temperature variations or temperature effects. So in order to further describe yung performance dun sa functional groups we are studying.
Sir, follow up po dun. Since meron pong problem sa data collection, ano po yung barriers po to overcome yung pagkukulang po sa data?
Okay. Thank you. Thank you for that question. Relatively AEM, there are, as mentioned earlier, there are, I can say, hindi pa ganun ka-develop yung models for AEM, particularly AEMWE, since most actually yung the modeling even yung sa PEM or proton exchange membrane water electrolyzers are based on fuel cells pa. So the assumption is parang the way fuel cells work, it's the same as what is what is happening on an water electrolyzer, since yun nga, very few math models pa yung nag-exist. And take note that the data we have used for this study are mainly just from published journals. So I believe yung the availability of the data, actually the recent data, as well as the even yung updated models, and even somehow medyo questionable din yung sa model build up din, because as I mentioned earlier, medyo it's more of tinitingnan na yung fuel cells. So yung parang the performance or yung para activity ng fuel cells mimics yung sa water electrolyzer, or actually it's the other way around pala. So yun.
Understood po. Thank you, sir.
Thank you.
All right, thank you so much, Sir July.
Thank you.
And it's about time for our next presenter. Our next presenter will tell us about low-dimensional clustering of GCMS chromatographic data using dynamic time warping kernels. This will be presented by the Hydro Resources Contractors Professorial Chair Awardee, Dr. Carl Ezra Pilario.
Hello, good morning. Thank you, Sir Charlie, for the introduction. And let me just share my slides. Okay, so are you now seeing the slides in presentation form?
Yes, presentation, sir.
All right, so I'll now begin. Okay, so at this point, I would like to sincerely thank the Hydro Resources Contractors Professorial Chair for the support that I have for this kind of research. So my research is again entitled Low Dimensional Clustering of GCMS Chromatographic Data using Dynamic Time Warping Kernels. So let me begin by GCMS. So I think we all know GCMS as engineers and chemists. GCMS means gas chromatography mass spectrometry, and is one of the many analytical techniques for characterizing the composition of samples. And the GCMS spectra contains information about the compounds that are present in a sample. So for example, if let's say you have the GCMS data of Philippine coffee. So as you can see, we have some peaks where compounds are present in this coffee sample. And the peaks will be different with different sources, origins, or types of sample. So for example, in coffee, if you have Robusta and if you have Arabica, then the patterns of the peaks will be different. Okay, so this is data sets that we can use for many applications in food and beverage analysis, in checking the quality of your products, in environmental analysis, checking the presence of possible pollutants in the environment, also in metabolomics, in checking the presence of metabolites in your samples, in criminal forensics, oil and gas analysis, if also you are working in the petrochem industry and you are using GCMS at the end of your pipeline, for example, and many other industrial applications. So that is GCMS. Now, if you take a look at the data sets from GCMS, the chromatograms can actually be seen as time series data. So in machine learning, when you say time series data, it is a set of or a list of values that are ordered in time. Okay, so in the x-axis, we have time, and the peaks represent the abundance of the compound that has been retained at that specific. Okay, so the higher the peak, the more abundant that compound is in your sample. Okay, and so with this kind of data, we can perform machine learning. Okay? We can use the GCMS data to cluster similar samples together. Okay, or you can input this time series data to predict certain properties from your sample, such as antioxidant properties, anti-tumor properties, and so on. You can also classify the samples according to the type. So, for example, if you give me a GCMS of coffee, then I can train a predictor that says, okay, this is a robusta or this is arabica. You can also use the GCMS samples to discriminate the samples as to their origin. Now, this last application will be the focus of my lecture in the following slides. So, in order to discriminate samples based on their GCMS data, many techniques are available. And specifically, if you are in the context of machine learning, we are looking at unsupervised learning techniques, specifically for dimensionality reduction, such as principal components analysis, and also for clustering, such as hierarchical clustering and k-means clustering. Although there are many other techniques that we can use, these techniques that are boxed here are the ones that we use because they're the most popular, and these are the ones that we want to build on in this research. So the specific samples that we tinkered for this research is bee propolis. Okay, this is interesting. Bee propolis is also known as bee glue. It is interesting because it has many properties: antibacterial, antifungal, anti-tumor, antiviral, antioxidant, antiparasitic, and so on. Now, in general, the composition of bee propolis is already well known, as shown in this breakdown. So balsamic substances, waxes, essential oils, pollen, and others. Okay. However, the composition can be different from different origins, and each of them have specific compounds present. And so what we did is we collected the pea propolis from 8 different regions in the US. So we have California, from Washington, Michigan, New York, Maine, Ohio, Alabama, Mississippi. Okay. And we collected 3 samples per state. Okay. Now, the goal of this research is that if we have the GCMS data of all of these samples, such as what I have shown here, then can we discriminate these samples based on their GCMS data alone? Okay, so without knowing where they came from, can their GCMS time series data provide us information on where they originate? Okay, so as you can see, the GCMS data here are very different from different origins. Okay, so that's where machine learning will come in. All right. However, it's not that simple because the direct application of machine learning to GCMS data using the current techniques is problematic because the peaks are not aligned. Okay, so that means if I take a look at the peaks, okay, the exact positions of the peaks are not aligned. And so if you have this set of GCMS data, visually you can see that they're the same. However, if you compute the similarity between these two data sets, they will be very different because they are not aligned. And that is where our contribution comes in. So our contribution is to propose the use of dynamic time warping. Okay, so what is this algorithm? It's an algorithm for measuring the similarity between two time series with alignment. Now, originally, DTW is used in speech recognition. So for example, if you have two different speeches from two different speakers, they are saying the same thing, but of course, they will differ in the speed of their words. So you can, one speaker will say doors and corners, kid, that's where they get you. And they're not aligned basically. So the DTW uh, is proposed to align the peaks from these two signals. Okay, and the algorithm is here, and this is what we incorporated into the traditional machine learning algorithms that we use. So our proposal is to incorporate the DTW as a kernel function or a similarity measure for our GCMS data. And the overall methodology, hence, is to gather the chromatograms, normalize the data, use dynamic time warping, then generate the kernel matrix, then use kernel principal components analysis, and finally discriminate between the propolis samples. Okay, now the end goal here is a projection of the data on two-dimensional space. So they will become points in a 2D space. And if the samples are similar to each other, then we expect the data points to be close to each other. So here are some of the results. From the chromatograms, we were able to compare the kernel matrices generated by the DTW kernel against the traditional kernels. And what we can see here is that the gram matrix from the DTW kernel is more, I mean, it's the best because it's closest to the perfect case. Why is this the perfect case? It's because every three samples are very similar to each other because they're of the same origin. And they are different from the rest of the samples because they are from different origins. Yeah. So if you remember, we have three samples from each origin. And so this is what is closest to the perfect case. And if you take a look at the projection in 2D space, you can see the clustering of these GCMS samples. And we can see that samples here from Alabama, from California, from Maine, they are closer to each other than they are from the different origins. And hence, our proposed method has the best clustering performance compared to the traditional kernel PCA and the standard PCA. As you can see in the traditional methods, it is very difficult to discriminate between, say, samples from California and Maine, also here in PCA. And statistically speaking, the silhouette index was highest in our proposed method, which measures the clustering performance. Our work was recently published just last week in the Expert Systems with Applications journal, and you can access them using this link. Okay. Now, we did not stop there. Actually, we also performed absorbance data. So we incorporated the technique to perform machine learning in absorbance data. And the PCA result is also satisfactory. And not only that, we also performed this not in B propolis, but also in Philippine tea. Okay, so we have many different Philippine tea, and these are their absorbance data sets. And the results of the clustering are also satisfactory. And not only PCA, we also used hierarchical clustering analysis. And the goal here is to be able to see how the samples from the same type of Philippine tea are the same. For example, here, mango, cranberry, and wild berry are all the same, more similar to each other than turmeric, lemongrass, and mint. And rightfully so, because these are all, as you have experienced, these kinds of tea are more minty. Okay. And the machine learning algorithm was able to elucidate that similarity. Future work, of course, we're interested in the chemometrics of other samples, honey, coffee, leaf extracts, also in samples of coconut, in biomass, and we can characterize and find similar samples of these other biological compounds. And you can also perform other machine learning tasks such as classification, prediction of their properties. Do they have antioxidant properties based only on the peaks of their GCMS? You can cluster them and so on. Also, not only GCMS, you can apply this in HPLC, fluorescence data, ATR, absorbance, and so on. All of these contain information as to their chemical composition, right? So you can automate the prediction of their properties using machine learning on these chemometric data. Also, other applications. If you have a sample that you project as well in the clustering, then maybe we can find novel samples, which is, for example, a new sample that we have not seen before. And that is very interesting to look at. Also, you can use that in industrial process monitoring, in the analysis of your oil and gas samples, metabolomics, again, environmental, and other food and beverages. Again, I thank the Hydro Resources Contractors Professorial Chair and collaboration that I have with Professor Elmer Rico Mojica from Pace University in New York, USA for the support of this research. So I am now ready for questions. Thank you very much.
All right, thank you, Sir Carl. Do we have questions from our participants? All right, we have one from Sir Brian Alaman. Okay, go ahead, Sir Brian.
Thank you, Charlie. Thank you for the great presentation, Carl. So my question here is, uh, is this different from the convolution, or can this complement the convolution, which you typically do to identify certain components, especially if you have samples in IR, for example, in GC, or in other spectroscopic technique and chromatographic technique that tend to have peaks na not easily discernible. You also use it kasi to identify. Would it be able to complement that, or augment the functionality of call this one deconvolution?
Yes, sir. Thank you for that question, sir. We're in the process of automating the comparison of these data sets. Yeah. And so if, for example, in a pipeline, you can have the deconvolution stage after performing our method. And hence, the automation of the whole process can be streamlined. So you don't need to have any human interaction in predicting the properties. So you have our method, then the convolution, then prediction of properties. Then you can have a completely automated pipeline.
Thank you, Carl.
Yes.
All right, and we have another question from Goran.
Hi, sir.
Yes.
Thank you for the really cool application ng further expansion po ng KPCA. Curious po ako sa PCA na part, kasi as mentioned po sa class, parang you reduce the number of dimensions.
Yes.
I'm curious po kung paano niyo po reduce yung like kung ano po yung initial number of dimensions sa pag-model, ano po yung naging final, and paano po yung process na yun? Thank you, sir.
Yes. Thank you for that question. So that's some details into the method. For example, you have a GCMS data. So here in California, as you can see, umabot ng 6,000, or the time series contains 6,000 data points. And that means all of them have 6,000 data points that we can compare against. So the initial dimensionality is around 6,000. And if you put that into PCA, each of them can provide information as to which of the data points are similar. And the 6,000 then reduces to 2. Okay, so all of the peaks will have an effect into where the final clustering of that data point will be in the 2D space. So if you see this, for example, number 14 different from number 13, and that is because there is a peak that is slightly different from that sample. That's the case.
Tapos sir, to follow up po, did you have like a script plot or something like that po to prove na optimal po yung two na principal components?
Yes, correct. I did not show it here, but we computed that the first two principal components has more than 90% variability explained.
Understood po. Thank you so much.
Okay, thank you.
All right, and that's all the time we have for Sir Carl. Thank you so much, Dr.
Thank
Pilario.
you.
And our next speaker will be talking to us about bismuth film-coated gold ultramicroelectrode array for the simultaneous quantification of lead-3 and cadmium-2 by square wave anodic stripping voltammetry. This talk will be delivered by the recipient of the Oscar M. Lopez Professorial Chair in Environmental Engineering. Let us all welcome Dr. Annalisa Rolion.
Hello, good morning. I'd like to first see to it that my slides are clearly shown in full view.
Yes, ma'am, we can see it
Okay.
clearly.
Okay. So I'm going to present this work, which is actually started by my ERDT student. It was conceptualized some time ago, but recently we have other students, ERDT students, who added to the work, and it's actually recently published. And together also with the help of other colleagues and with the financial support of ERDT. And this is also presented for the Oscar M. Lopez Professorial Chair in Environmental Engineering. So I'm going to present bismuth film-coated gold ultra microelectrode array for simultaneous quantification of lead-2 and cadmium-2 by square wave anodic stripping voltammetry. So this is the article on this. And the reason for the motivation for this research is that we wanted to develop something that can measure with simplicity heavy metals in drinking water resources. Lead and cadmium, for example, impairs brain, lungs, and other vital organs and can impair fetus development. The World Health Organization has set a maximum allowable concentration of 3 micrograms per liter for cadmium and 10 for lead in drinking water. And it is important to also measure it in environmental water samples which are used as drinking water resources. We need sensors for determination of heavy metals because equipment where we have sensors as the component that determines the metals, these are quite simple compared to other instruments which are expensive, complex, requiring complex preparations, high maintenance, and highly skilled personnel. We employ here anodic stripping voltammetry, and this method is an electroanalytical technique that provides high sensitivity for trace metal analysis in various environmental matrices. So for instance, here you can see that if you have a substrate or it's a solid, there's a working electrode deposited in here. So, and then there is a pre-concentration step wherein the metals from the solution or the analyte metal from the solution is electrodeposited. So it is accumulated onto the surface of the electrode by applying a sufficient negative potential through which the target analyte metal is reduced, and it forms an amalgam with the electrode. And because of this step, this technique becomes highly sensitive because you can actually do something about the pre-concentration step. So the more metals that you are able to pre-concentrate in here, the better it will be. Although, of course, there may be some limitation as to how you can increase it further. And then in the second step, that is the stripping step, the metal is stripped off from the electrode, and that is through applying a stripping potential, and it yields a current response linear to the metal concentration. So which means that if you have here, if you did the stripping scan, you will see a voltammogram where the peak potential, the potential corresponding to this peak, gives us the identity of the metal, and it should be unique to the metal, and then the intensity or the peak height in terms of the current gives us the an indicator of the metal concentration. So this procedure enhances both the sensitivity and selectivity towards the target analyte. And recently also there's this development of microelectrode which are quite small compared to the previous kinds of electrode. And because of the small dimension of the microelectrode, it improves the signal to noise ratio. However, if you just have one microelectrode or ultra microelectrode, the signal can be very small, so that you want to amplify that signal, and that means the use of ultra microelectrode array does this. So here, this is actually the ultra microelectrode array that we use in the study. So this array is composed of gold ultra microelectrode array, 2 millimeters by 2 millimeters, contained in 400 gold microdisc, and each disc here has a 5 micrometer diameter, and these are 100 micrometer apart, center to center distance, and it is built with an counter electrode, which is this dimension given here, and it is placed 0.5 micrometers away from the working electrode. And we applied square wave anodic stripping voltammetry. So this is the square wave voltammetry, where you can see here that there's a step increment in the amplified in the amplitude of the wave, and the frequency is given as 1 over, or the this length, this is the reciprocal of that is the frequency. And these are the parameters of the square wave anodic stripping voltammetry. In this study, we have in situ prepared the bismuth film coated gold electromicroelectrode array, which means that we deposited the bismuth into the gold ultra microelectrode array. And we use it as a sensing device for cadmium and lead detection in water. The samples were analyzed. I mean, the study was square wave anodic stripping voltammetry. And we determined the effects of various parameters like the deposition time of the bismuth and the concentration of the bismuth and the acetate buffer concentration, the pH, the square wave frequency, amplitude, and step potential. And we also look into the interferences of selected ions like copper, nickel, sodium chloride, and also benzene. We look at the effects of this on the current potential or the current peak intensities of the target metal ions. And we optimize the square wave anodic stripping voltammetry parameters, including frequency, step potential, using the Box-Benken design, and look at the interaction effects. So here is the setup. So this is the system where we have here the ultra microelectrode array. This is the working electrode. And then we have the platinum as the counter electrode. And then we have here the reference electrode. And for the working electrode, we have the urea, the gold urea. And in step 1, bismuth is electrode deposited on the gold urea. And in step 2, the metal ions that are deposited in the film of bismuth or is stripped using anodic scan. And that gives us this signal of the current versus the potential applied. So in the first experiment, we can show you here that we have the current versus time. That is the pre-concentration time where bismuth is where the metal is concentrated or deposited into the film, into the working electrode. And then we can see here that as the concentration increases, the current also, the current height or the peak height also increases. So here, and also as the time, the pre-concentration time increases, we can see increasing current. So actually, if you can see in here, even at 600 seconds time, that must be enough, because even beyond that, we still have a linear relationship. Because we don't want that we are working on an area or on a range wherein it's already becoming nonlinear. And for the effect of the bismuth concentration, these are the voltammograms. This is for the lead and for the cadmium, and these are at different concentration of the bismuth 3. And plotted against the concentration of bismuth concentration, plotted against the bismuth concentration is the current peak intensity. And we can see here that near this area seems to be the maximum, or the maximum current intensity for lead and cadmium. By the way, we use a higher concentration of cadmium compared to lead because cadmium has less affinity and therefore less diffusivity. So we increase a bit the cadmium concentration. And if we're looking at the bismuth to metal ion ratio, so it is the metal concentration. This is for cadmium, and this is for lead. And the bismuth concentration is 500 micrograms per liter. So if you have here 100, that means 500 over 100, the ratio is 5. And if we have here 500 over, the ratio is 5 in here, whereas here the ratio is, what's this, 50, 500 over 50, it's about 10, no? So we can see here that as the metal to ion concentration increases, that is going from here to here, you can see the stripping peak area decreasing. And for the effect of the acetate buffer concentration, we can see here this that the stripping peak area has a maximum somewhere in this range in concentration of the acetate buffer. For cadmium here, around 0.001, and for lead, it is also between 0.001 and 0.05. So therefore, if we're going to simultaneously determine lead and cadmium, it must be somewhere within the 0.001 concentration of acetate buffer. And the effect of pH is given at the right side. We have here the peak area, the stripping peak area versus the pH. And as we can see, as pH increases, the peak area also increases. However, we did not determine any more beyond 4 because we take note also that beyond 4, there can be complexation of the metal ions, for example, lead, and that can be not good for the analytical determination of the metals. And then for the effect of the square wave parameters, like in this case, the frequency, you can see here the current and versus the frequency. And it seems that the frequency, it is shown here that the frequency is somewhere between 13 and 17, both for cadmium and lead. And also, if we increase further the frequency, you can see also that the base can be broadening also for the voltammograms. And for the effect of the amplitude, we can see here that for cadmium and lead, amplitude between 50 and 65, or even 45 to 65, maybe the optimum current amplitude, giving the best current values. And for the step potential, we can see here that it's somewhere between 9 and 13. The step potential should be to give us a good current. And for the effects of interfering ions, we have here copper 2 at 100 and 500 micrograms per liter of the concentrations of copper 2. The peak area, there are no peaks, or there's no peak that can be seen, both for the detection of the cadmium and lead. Whereas for nickel, at 105 500, for cadmium, there's about 54% reduction in the peak area and 80% at 500 micrograms per liter concentration of nickel. But for lead, there is less reduction in the peak area, at 100 micrograms per liter, but higher for the 500 micrograms per liter for lead. It's about 50%. But for sodium chloride, the reduction in the peak area is higher for the lead than for cadmium, both for the 100 and 500. And for benzene, there's also peak reduction in the peak area reduction for the cadmium and lead. But nevertheless, even if we can see this peak area reduction, still we are able to, we can actually correct this if we also know what will be the relationship of the ion concentration with the peak area reduction. But you can differentiate between the two metals, and you can differentiate also between different concentration because of the linearity of the current versus the concentration of the metals. And for the optimization, so these are the contour plots of and giving us the two parameter interaction, for instance, frequency versus amplitude, or frequency versus step potential, and amplitude versus step potential. You can see here that for the frequency, it's somewhere between 13, 15, and step potential near 9 or 8, 9, 10. And that's also true for lead. And then for the amplitude, it's somewhere near this. And for the optimum conditions, so the empirical model was generated from the experiment. And the optimum conditions, that means for maximum current peak areas, were 14.76 hertz for the frequency. For the square wave amplitude, it is 50.1 millivolts. And for the square wave step potential, it is 8.76 millivolts. And these optimized values were obtained, of course, from the empirical model. And also, if we use this, we are able to determine that the cadmium concentration for lead and the concentration, or the peak area will be 30.35 and 22.59 for cadmium and lead. And we validated this and giving us similar values, very close to the predicted values. And for the calibration curve, the peak area here is plotted against the concentration of the two metals, the red one for the lead and the black one for the cadmium. And then we can see that we were able to determine that the slope of the linear fit, which gives us the sensitivity, is 0.58. And for cadmium, it is 0.67 NC per microgram per liter for lead. And the limits of detection were determined to be 5 for cadmium and 7 micrograms per liter for lead. And this actually overperformed other bismuth-based electrodes in the simultaneous quantification of trace lead and cadmium from water matrices. So as conclusions, this work demonstrated the performance of bismuth film ultramicroelectrode array for the simultaneous determination of cadmium lead in water by square wave anodic stripping voltammetry. The optimal experimental conditions are 600 seconds and 900 micrograms per liter for deposition time and bismuth concentration. And for the low acetate buffer concentration at pH less than the pKa of acetic acid resulted in high response for the current peak area for both cadmium and lead. These ions interfered with the peak area responses for both cadmium and lead, and the optimum conditions, the limit of detections already mentioned a while ago, and with a relative standard deviation of about 10 or 12% for cadmium and lead. So the use of bismuth film ultramicroelectrode array in SWAS SB for the detection of cadmium and lead in water is a promising alternative to existing analytical methods with slow detection limits and simple setup. With this, we'd like to acknowledge the Department of Science and Technology through the ERDT and the National Research Foundation through Ministry of Education for providing the extension of the work, and the Oscar M. Lopez Professorial Chair in Environmental Engineering. Thank you very much for your attention.
All right, thank you so much, Dr. Leon. And our next presenter is not around, so unfortunately we do not have time for questions. Or I guess we can entertain a question. Anyone from the audience? Since our next presenter is not around.
Sige, Charlie, yeah, I have a question. Hi, Ma'am Annalie.
Hi, Brian.
Ma'am, a related question to that is, for example, often you find these metals, for example, occurring as a multi-component. Oh, you have mixtures of these metals. So would there be a chance? Hopefully I did not miss it. That we can account for the effect on the what do you call this one, on the sensitivity and the selectivity, because sometimes the metals tend to mask the other metal, making it undetectable for the other, when you're using new sensors.
Yeah, actually, that is indeed a problem when the other metals are present. But I think it can be tried. What will be the, at what concentrations of these other metals they can be detected using the array. And then, of course, there are still other things that can be explored in order that we can expand the detection, for example, for other metals. And the other metals, depending on the potential will give their identity. It's just, a limitation maybe is that when there are two metals with very, very close potential, the peak areas are very near each other. The peak, the potential where they can be seen. But in terms of further improvement of the design, it can also be an improvement on the ultramicroelectrode array, because we can still increase the signal or increase the responses through the design of the ultra micro electrode array. Some other researchers also look into other kinds of material that can be used in order that there will be no interference with the working electrode in terms of sensing the response. But we have not explored that in this study.
Thank you, ma'am.
All right. And thank you so much, Dr. Leon.
Thank you.
And right. And our last presenter for this morning is Dr. Brian Alamani. He is the recipient of the Lagman Family Professorial Chair in Engineering, and he will talk to us about zinc ions modify calcium oxalate growth by the zinc transformation of crystal surface termination. Let us all welcome Dr. Alamani.
Thank you very much, Dr. Montealegre. Thank you very much, everyone, for attending, for joining us this morning. So for this session, I'll be sharing with you the work that we have done, also in partnership with Curtin University through Julian Gale and Jeffrey Reimer at the University of Houston. So what I'm going to present to you this afternoon appears to be a fundamental study, but this was inspired by a medical question that we've been trying to answer for about 3 to 5 years, similar to the length of my PhD. So this work was primarily lifted from a published work, which was published last May 2021 at the Journal of Crystal Growth and Design, authored by me, Julian, and Jeff. So I would like to start by first acknowledging the support provided by UP EARDFI through the Lagman Family Professorial Chair in Engineering. Without this support, it would have been impossible, especially during the time of the pandemic. I'm trying to piece together the story that we would like to present for this morning. Also, I'd like to acknowledge the support provided by the UP system through the Enhanced Creative Work Research and Development Grant, and also the support from my collaborators from Curtin in Australia, in Perth, as well as from University of Houston in the United States. So I would like to start first by looking at the common disease, which hopefully a number of us, or maybe we know someone who have had it, kidney stone. Some call it the typical pathological biomineral. So for kidney stone formation, about 20% of that, about majority of that is primarily calcium stone, at least in the case of the United States. About 70 to 80, about 20% of that, 70 to 80% is calcium phosphate, and a majority is calcium oxalate stone. So you will see here an illustration of calcium oxalate stone on this side, taken from actual patients, which is presented in this paper in Nature Reviews Urology. So to be able to understand it, what we decided to do is look at it on a single crystal level. So by looking at the way of a single crystal level, a form of calcium oxalate, which can be synthesized in the laboratory, forming this characteristic hexagonal habit, you'll be able to try to emulate some of the processes and then try to put it in vitro and identify what could be possible interactions that can lead to changes in the growth of that crystal, which is the main component, which is the one that assembles to form ultimately your calcium oxalate kidney stone. So here, to be able to change and try to control the growth, we tend to use a couple of what we call modifiers. And the simplest one that we've been using, which is the subject of this presentation, would be ions. In particular, we concentrated on zinc. So in this case, ions tend to change the way how a crystal is growing, but that is still a subject of many studies, and it has developed really significantly throughout the years. And we are happy to contribute to understanding those mechanisms. Another type of modifiers that we are using are actually molecules, pretty common because most of the drugs designed to try to address pathological diseases, pathological crystallization rather, are actually molecules. Also, we have macromolecules, which are naturally occurring. So for example, the human body, the reason why we don't have ectopic calcification, or at least we don't have calcification of our blood vessels, it's because of a natural osteopontin phosphopeptide, which is naturally produced in the body, a natural modifier that regulates the crystallization of calcium phosphate in the human body. So here I'm going to present to you some of the results that we've gathered. So we did this in vitro, so in a test tube, using a biomimic solution that mimics the ionic strength of the average ionic strength in urinary systems. So what you see here is the first on your panel is a figure showing a microscope image of a typical calcium oxalate crystal. And then you see that we started progressively adding zinc, where D is 40 micromolar of zinc. Then we added 100 micromolar of zinc, and then we also have 140 micromolar. As you can see, the crystals, you have fewer and fewer crystals growing, and then at the same time, you have larger and larger crystals. And interestingly, at some point, you will see large, what we call intergrowth forming, which is something that has been seen in literature and that has been rather presented in literature and has been presented as well as potential precursors of other types of stone, or a bigger type of stone in the medical, which becomes a medical concern. So we started to concentrate as well on these interesting morphology that you see here. This one, the intergrowth. So we tried to do ex situ time-elapse analysis, try to see whether they actually grow. So we had here a time-elapse visualization taken using scanning electron microscopy to try to see where those crystallites originate. And they appear to originate on one of, a young crystal here. And then you see that this one protruding towards the C direction. And then slowly it will evolve, forming this dendritic-like, or what we called as intergrowth or inner growth in our studies. All right, so next we also try to look at the way, how fast are these crystals growing? Do they grow really fast? Do they grow really slow in the presence of zinc? So what we did is we used in situ ion selective electrochemical measurements, which tries to detect the presence of free calcium ions in solution. And then the depletion of that ions, the disappearance of those free ions, is commensurate to the growth of the crystal. So what happens here is that if you, for example, introduce more and more inhibitor, like this one, we are introducing here zinc, what happens is that the rate goes down. And we tried to represent this represented this in terms of a relative growth rate. What happens here is you have the relative growth rate, which is the ratio of the rate versus that of the ratio of the rate of the crystallization in the absence of zinc. So definitely you start with 1, which is your control, and then slowly it goes down until it reaches about 50% at 140 micromolar, about 50% reduction. So suggesting that zinc is actually reducing the growth rate of the calcium oxalate that we are trying to grow in vitro. Okay, so at least it gives us an idea that zinc can influence the nucleation. Zinc can also influence the growth. At least we have an idea, but then at the same time, it tends to promote the formation of intergrowth, which all of these observations are found to be consistent with what has been published in the medical literature. Now, let's try to go step back a little bit. How does a crystal grow? How do we build a crystal? So here you can see an example of a causal crystal, an illustration of how, say, a crystal, it's like a Lego piece. Imagine having a Lego piece and you try to build one by one the content of that Lego piece by using some small Lego parts. Okay, you start to build them. So interesting, a crystal has different sites, and we have here a step. Imagine the step in your staircase, and then you also have a kink site. Imagine the corner of a room, and then you also have a terrace, so which is comparable to a terrace that you have extended from your house. So now, macroscopically, or at least in experiments, how do we control this? So we do this by changing many parameters, such as supersaturation, which is the driving force of crystallization, by choosing a different solvent, switching temperature, or in my case, and in the case of this experiment that we are presenting, changing the modifier and choosing a certain modifier. And you can also tweak it using time, which is very common in hydrothermal synthesis for zeolites, for some other like metal oxides, you tend to use time as one of your key variable in trying to optimize the synthetic, the crystallization process. So in reality, a crystal grows in an environment that is not pure. So it could be influenced by what we call impurities, and then these impurities tend to disrupt the growth of that crystal. And here are some of the mechanisms by which it operates. So the first one is step pinning. So what happens here is that you have a crystal, you have the steps, your what do you call this one? Your inhibitor or your modifier tend to pin on the edge of the steps. You also have a modifier, which is in a way pinning on the kink sides. So that's the kink blocking mechanism. And recently discovered in our group back in Houston, strain-induced dissolution, where the presence of the modifier tends to put a strain on the crystal surface, therefore in reducing inducing dissolution. All right. So to be able to understand all of these, a very important tool that we've used for several years and up to 2019, 2020 was an in situ atomic force microscope. So this microscope allows you to sample or to image a sample in the presence of a flowing liquid. And that allows you to see in real time how a crystal is growing all the way down to a molecular and even atomic level. So far we don't have this in the country. I've used this one in the United States and the other one also in Japan. So this is at least a model. One of the models that I used was the Cypher, which is the instrument that, it's an environmental scan AFM. Okay, so here what I will show you is the way how this calcium oxalate crystal, particularly the basal surface, grows. And then this movie, I hope you can see it. So it shows you the way how the crystal is propagating. This is in the presence of a growth solution flowing. And this was the movie I generated a couple of years ago. So now I'm gonna show you the influence of zinc. Okay, so here I have here at the smaller scale bars, 100 nanometers. So this is in the absence of zinc. So it grows the usual triangular mode. Now I started to add zinc. So what happens is that there was a change in the morphology. So you now have a circular. Characteristically, if you try to image this, both of these are still calcium oxalate crystal. Just so happened that the second movie shows you the presence, is the morphology in the presence of zinc. So now we started to try to decipher everything, and we made snapshots of those events. So here is an illustration on the first column, on the first row rather, from A to D. You see here that the growth in the absence of zinc. So it's the usual one. Okay, you have the triangle, the almost triangular kind of growth pattern emanating from the dislocation center. Now, in the presence of 50 micromolar of zinc, what you will see here is that it started to have step bunching at G and H, and then you will see the slowly changes into sort of a circular step shapes of the step. So as a bonus, what we also did is we tried to image the lattice, the way how the atoms are arranged and would they be influenced. So we see some slight change in the for example, as you can see, I and K, you have no zinc for that. And then J and L shows you in the presence of zinc. So there's a little bit of a change in the lattice, but we couldn't really assign the atoms here. It would require another study that would have to work on the molecular modeling aspect as well. Okay, so now what we did is that we tried to identify how does zinc inhibit or control the growth of the crystal. So based on this model presented by Bliznakov, we found out that it most likely is step pinning. And as we've recalled earlier, step pinning, the characteristic of step pinning is the presence of corrugations on the step edges of a growing crystal that is influenced by the modifier. And this is also another information that we got, that possibly because of zinc, there are changes on the surface terminations. And these surface terminations, you might have calcium exposed, say oxygen are exposed, some of hydrogen, carbon is also exposed. So it depends. So that is one thing, but this is still an ongoing study. We wanted to know what exactly those particular terminations are. And lastly, ultimately, what you've seen here is that the presence of zinc can actually alter the surface termination. It can lead to potential changes on the shape of the growing crystal, or possibly the growing layers of the that will ultimately result into your final crystal. And to corroborate our study, we partnered with Julian from Curtin, and then he mentioned to us that zinc actually prefers to stay on the interface, and that can definitely influence the overall crystallization process, because crystallization itself is inherently an interfacial process. And just to summarize, first, we found out that zinc influences calm crystallization through two modes of action, influencing nucleation and growth, as well as facilitating the formation of intergrowth. Secondly, we were able to capture those possible changes on the surface terminations by corroborating AFM and density functional studies. And we are currently having ongoing work on different ions and different molecules and macromolecules, not just limited to pharmaceutical or say to the medical field, but we're extending it to, for example, construction. We're extending it to development of catalysts and other materials. And ultimately, I will end with this one, that by trying to control the pathways of crystallization, you may be able to come up with new materials, you will be able to come up with different functionalities, and then you can find different applications across different industrial needs. With that, thank you very much. And I hope you're able to able to learn a lot from this short presentation. Thank you.
All right, thank you, Dr. Lamani. And we have questions from our audience. Okay, I don't see any raised hands, and ako na lang magtanong, sir. My question is, I saw some phase transformations earlier in one of the slides. Is that due to the presence of zinc or other materials?
Which one? Sorry, I wasn't able to pick it up.
I just I saw a transformation from C from the monooxalate.
Are you referring to this one?
Yung full crystals. Or tama ba yung natanda?
Medyo choppy. It's a little bit choppy.
Or did I recall it right na nagkaroon ng transformation from one crystal phase to another?
Okay. So there were no transformation from one crystal phase to another. Though it's not presented here, we did subject this to XRD, and there was no transformation in the crystal. If we came up with a new polymorph, because we've also seen in DFT that the zinc actually does not get incorporated into the bulk crystal, into a single crystal that we are growing. It just resides on the interface, and once you wash it with water, the zinc just goes away, and you can actually recover back the original morphology, even though the original crystal, even though there's a slight change in the surface morphology.
All right, sir. All right, thank you so much. And okay, we do have some questions from first from Ma'am Marge and another for Sir Valreyes. Let's start with Ma'am Marge.
Yeah, Sir Brian, yung question ko is hindi talaga sa parang in terms of health, like when you are taking vitamins that have zinc, like so ibig sabihin sa body, ano yung effect niya with regards to the stones? Parang can we say na should we not take zinc laden vitamins or ano?
Okay. So that is, I will be cautious with this one. Thank you for asking the question, Marge, because this is also a question we got before. when we studied this work, when we started it, we just look at the crystal growth aspect, and then how zinc can try to modulate the formation of calcium oxalate. Now, what we notice is that at least in the United States, the concentration of zinc supplement is around 550 micromolar. The zinc supplement, one tablet that you get from over the counter, and then the NIH limit that was set in the US was only 40 micromolar. So we mentioned that to our audience, and then we are not yet sure whether it will definitely lead to that growth, that unwanted growth. But if it becomes if it's too excessive, it might possibly. But again, the body has a way to process this metabolically, and that is one thing that we haven't explored yet. We've initiated one with a urologist based in Chicago to help us with that one.
Thank you.
Thank you. Yes, Sir Val.
Yes, Professor Brian. First of all, this comment is this: your paper and other papers I think presented show a natural affinity between chemical engineering and the medical science, which is something that is always good. Yeah. But having said that, and this is probably a kind of a follow-up to the previous question. Do you see potential for offering this research to pharmaceuticals who might be interested in developing drugs to help prevent stone forming, which resonates with me because my wife is a stone former, so I'm sure she'd be interested in your answer. Thank you.
Thank you very much for the question, Sir Val. Actually, yes. We only answered the question that we answered in this paper was a fundamental question, because a lot of people in the medical field, at least in the case of the US, when we try to look at the literature, medyo iba po kasing stone composition sa Philippines, but we can still in a way apply a similar approach. What we notice is that sometimes supplementation is a way to address zinc, what do you call this one, stone issues, because again, it's also a metabolic and there's a dietary way to manage your consumption. So we can definitely offer this, the ideas that we have. I, in a way, started to work with a group of trying to initiate contacts with UP Manila to help me, get on the medical side. It's also the reason why we did not have any ideas on patenting, for example, the zinc work. What I've patented together with my former advisor back in the US is the use of phosphates to try to regulate stones, because we have them available on the market, and there might be attempts they are not yet on the level that you can use them as a drug, but there are nice simple molecules that are more effective than zinc in terms of reducing the growth. And there's also a weight loss supplement, which was it's hydroxycitrate. You can buy it Health and Wellness, the one that we I forgot the name. That's a store dito sa Manila. It's Garcinia, Cambodia. It contains hydroxycitrate. About 60% of that is hydroxycitrate, which may potentially, even though it's claimed as a weight loss supplement, it was found out to be a potential way to manage recurrent stone formation in certain patients.
Thank you, Prof. Brian. Chicho Mantaring is also here, so I think if you'd like to connect with Erdfi on this, I'm sure he'd be happy to hear from you.
Thank you, po.
And Sir Brian, we also have another question from the chat, and Dr. Delen asked if have you also done or are planning to do experiments on the dissolution of calcium oxalate or the phosphate?
Okay. Thank you, Ma'am Babylin. Actually, we've already submitted for publication a paper on using what we call polyphosphates to dissolve oxalates and phosphate stones. And we found out that these polyphosphates have the ability to reduce that. Experimentally, we found them to almost be 100% efficient. So the submission of the paper only was done this 2021 around July 2021. Because we need way back 2018, we need to have it filed. So yes, ma'am, we have we filed the patent. The patent is already with the US Patent Office. We filed it and then we already published the paper, and we are planning to actually pursue more on that field of use of dissolving, if possible, dissolving the crystal, the unwanted concretions inside the human body. Obviously, we don't want to dissolve the bones, pero it's the kidney stones and other calcifications which should not be present inside the human body. One example of calcification I'm referring to is this is a little bit of a challenge for us though. Is atherosclerosis, cholesterol accumulation, which is also a type of, it's not calcification, but it's a type of concretion that we're trying to hopefully address using maybe the polyphosphates.
Wow. Thank you, Sir Brian. That's very
Thank you,
exciting.
ma'am. Thank you po.
All right, and do we have more questions? Okay, I don't see any more hands raised up, and thank you so much, Sir Brian. And that concludes our morning session. Thank you so much for your participation, everyone. And we do have another session this afternoon. Before we all go, can we have a little photo op if it's okay for you to turn on your videos? You can stop sharing, Sir Brian. All right, and I see, okay, I see a lot of cameras being turned on. Let's wait a little bit for some more people. Okay, this is a very nice turnout. Okay, I'll start taking them now. Okay. May habol pa po. All right, 1, 2, 3. How do you do this? Or picture na lang, Sir Carl. I don't know how to do it here.
All right, sige, teka. I'll full screen. Okay, print screen ko na lang. Okay, 1, 2, 3. All right. Okay na po.
Thank you and congratulations to everyone.
Thank you, and maraming salamat sa mga dumalo. In the afternoon, we'll start at 1 p.m. and we'll end at 4:15. And hopefully, tayo pong lahat, all of us will return for the afternoon session. So see you again later.
Bye, everyone.
Bye. Happy lunch. Thank you.